Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
So our next session will focus mostly on the sort of educational aspects of the center and putting education into computational thinking, some of which I described earlier. And so we'll start with Guy Blalock.
Okay, so I'll talk about parallel thinking, and this is obviously motivated by the notion of computational thinking from the name. And this first arose, in fact, this came out of the early days of the Computational Thinking Center and was one of the original projects. So we all know that parallelism is basically you can't buy a processor nowadays which isn't parallel. It doesn't have multiple cores, and of course there's lots of parallelism even within the cores. You can go to Amazon, you can buy a 16-core chip, you can buy 8 and 4 and 2-core ones. You can also go to the Dell site, and they'll put 4 of these chips together in a little slide-in rack-mounted server like this. So you get, I guess that's 4 times 16 is 64 cores. You can buy a GPU, all sorts of flavors of GPUs, and these have up to 1,000. In fact, the new ones even have more than 1,000 cores on them. Interestingly, of course, your cell phones. Nowadays, new cell phones, Samsung is advertising, a 4-core one, and this was in over about a year ago, and immediately Intel put out a news announcement that says, forget 4-core, 48-core smartphones. In fact, it looks from the date, it looks like it was a day before, but that was just so anyway, so we're going to get 48-core cell phones. Or if you're a hobbyist, you can buy one of these. This is sort of the follow-up on the Raspberry Pi. This is one of these things you buy for $100, and you can play around with. And they have 4 cores. So pretty much everything has multiple cores. So we want to make use of this. And the idea of parallel thinking is we want to do this in a way where we're sort of raising the level of abstraction. And this comes from a realization that if you look at most of the way that parallel computing is being taught out there, it's very low level. It's very much focused on a particular programming language, particular machine or something. And so the idea is, in the same way that Jeanette wanted to say, what are the core ideas of computation? We wanted to look at what are the core ideas of parallelism. And the premise here is that, first of all, if you start raising the level of abstraction, a lot of things are parallel anyway. So parallelism is pretty easy. It's not a complicated topic. Furthermore, we've sort of been brainwashed into thinking sequentially, so we really have to step back in order to figure out what this parallelism is. And lastly here, there aren't that many ideas in parallel that we can sort of extract a set of core ideas. I don't know. And that, so what are these core ideas? And ultimately, the goal, of course, is to put this into education, into our curriculum. Just a side note here, there's lots of different ideas of what parallelism means. I'm going to be focusing on a somewhat limited form here, is when we have things running concurrently, it could either be because your environment is naturally concurrent, in which case this has been true in operating systems for many years. We've had servers running, and I don't know, a web server could be actually run on a single processor, and you had to have all sorts of incoming demands, and so there's concurrency coming from the environment. So I call that sort of a concurrency, versus having just one problem you're trying to solve. I know you're trying to render some image, and that's just a single problem we're trying to solve. So that's along this axis between sequential and concurrent. And the other axis is if you're running it on one core or multiple cores, one processor or multiple processors. So what I'm going to be talking more about today is running on multiple processors, but running what sort of a deterministic parallel thing. So I'm not really talking about interactive environments. I'm talking about you've got one job to do and you want to do it as fast as possible. And so that's what I mean by parallelism. And at the end, I'll talk in terms of in future sort of work and what we could do in this space here. Okay, so what is parallel thinking? Again, it's the idea of what are the abstract ideas in parallelism. So in particular, it's not particular programming languages. So it's not about teaching CUDA, OpenMP, Hadoop, etc. Okay. It's not about particular machines. So it's not about a particular GPU processor. It's not about a particular, I don't know, a multicore or something like that. Okay. It's not about distinctions such as data parallel versus task parallelism. It's not about Amdahl's law, and I'll say something about this. Amdahl's law is too fuzzy of an idea. It's not about libraries versus languages versus automatic parallelization. I claim that once you've figured out that your algorithm or your computation is parallel, this is really just an implementation idea, whether you use a library or a language or you rely on some automatic parallelization. And it's not about domain-specific languages, and it's not about taking your sequential code and trying to squeeze it into some sort of parallel toolbox. Okay? What it is about is understanding dependencies, and I'm going to be more concrete. This is being a little vague here. Is understanding the dependencies in your computation and sort of breaking away from this idea of doing one thing at a time and really understanding what depends on what in a computation. And that's where the parallelism is going to come. It's talking about potential parallelism as opposed to actually how it runs on real processes. So you're going to expose the full parallelism, and then a scheduler presumably would map that onto processes. It's understanding computations in terms of the total work they do, which is sort of what the sequential time would be, and the span, which is once you think about it in terms of dependencies, this is the critical path of dependencies. Other key ideas of work efficiency. It's understanding the sort of key algorithmic techniques to get parallelism, and it's also this is all in the context of dynamic parallelism, where we're generating parallelism as we go. So my favorite example, and if you've seen me give a talk before, you've probably seen this example before, but I think it's very telling in terms of abstraction, because here's a piece of code from a book that was published in 1974. Okay, it's Quicksort. They had no motivation to talk about parallelism. This book is not about parallelism. It's about the design and analysis of computer algorithms sequentially. But they had the, forethought to write it in a very high level. So they write this code at some high level, and it's written at a high enough level that it really is a piece of parallel code, okay, or it's a parallel algorithm, and that so there's some notion that there's some pureness about the parallelism here because it's not, we're trying to map this onto some machine or something. And so why is this parallel? Well, it's parallel because obviously we can make the two calls to quicksort in parallel, and it doesn't even say in the code that we do one and then we do not, so they do the other. So they even have, in some sense, the forethought of saying, just saying that this is how you put things together rather than the execution order. So you put the results of the quicksort of the smaller and the greater elements with the equal elements in the middle. But the other thing here is you can also, you've got this pivot and you have to compare it to all the rest of the keys. You can also do this in parallel. And there's nothing in here that says we've got some loop that goes over the keys and compares them to the pivot. And so this itself can be done in parallel. We can do this giant comparison of all the keys to the pivot and then select the ones which are smaller, larger. Of course, this doesn't tell us much about, it's just vaguely parallel, but there is a very nice way to sort of then make concrete exactly how parallel this algorithm is. And what you can do is to go back to the dependencies. So if this is sort of a dependence graph along here, so we can do these two things in parallel. So they depend on first splitting based on the first pivot, and then we have to split based on the pivot in here to generate the next two recursive calls. And then these blocks are supposed to show that we can actually compare the pivot to the keys in parallel and then somehow do the splitting. And it turns out you can do that in sort of a log n dependence, and I'm not going to go into detail on that. But at the end of the day, you can show with an expectation or even with high probability, if you pick a random pivot, that the overall path, longest path of dependencies is something like log squared n. Okay, so you get a nice theoretical bound on sort of the critical path of this algorithm. You can show the work is n log n. In fact, the work is identical to the sequential algorithm, because in a sense it is the same as the sequential algorithm. We've just raised the abstraction to ignore the false dependencies. And then we can define this notion of parallelism, which is basically the work over the span, which gives you a sense of how many processes about you can make use of. Okay, so this is the sort of the level of abstraction that we're talking about when we're saying parallel thinking. It's not tied to a particular programming language. It's, it's written in pseudo. In fact, I'm using here a piece of pseudocode that was written not even in the context of parallel programming. And it's, using high-level notions of dependencies, et cetera. Okay. So we sort of spent some time thinking about, well, what are these high-level concepts in parallel programming? There's a list here. There's, dealing with collections is an important idea where you, instead of thinking about, mapping loops that go over every element, we think of operations across a whole collection. So mapping a function across a collection. Reducing means, like, for example, summing the elements of a collection. There's a scan operation. There's various operations that you do in collections. There's sequences, dealing with sequences or ordered sets and tables, a lot more. So it sort of gives you much more of a Python or a MATLAB flavor of programming, right, where you're dealing with whole sets or collections as opposed to a Java or C flavor of programming where you're thinking of writing loops over things. And so this parallel thinking almost goes in the same direction as other sort of changes we're making, which are moving towards languages such as Python, et cetera. There's this notion of nested parallelism work span. There's a lot of sort of algorithmic techniques which turn out to be very useful in parallelism, which are also useful in sequential computing, some of them. So divide and conquer, of course, we know this. The thing is that it's even more useful in parallel computation than in sequential, because it has the additional advantage of being able to do the divided calls in parallel. This idea of contraction, which is something that doesn't show up so much in sequential computing, which is you take some collection of values, you contract it to something smaller, and then contract it. It's like divide and conquer, but you're only making one recursive call. There's a lot of use of trees, dynamic programming. Anyway, we've gone through this and sort of figured out what the core idea is in parallel computing. And we put this together into a course, which we now teach, which is this 15.2.10. Okay? We teach some of these concepts actually in the earlier course in 15.150. So if you remember Randy's picture, there was this 15.122, 150 that led up to a data structures course, which was this 15.2.10. Okay, and we've done that in terms of teaching, and we've actually got quite a complete set of notes, and we're starting to actually write a textbook in this. There's also a research component of the parallel thinking, which I'm really not going to talk much about today, except on this last topic here. Okay, so 15.2.10. So we've now been teaching it for 3 years. So this is to give you a sense of how it's going. They're taught to second semester freshmen and first semester sophomores. We now have, for 15.2.10, we have over 250 students a year. In fact, I think if we take this past semester and the next semester, it's going to be over 300 students. We only have 140 majors. Okay, so this is a course originally designed for majors, and we get more than twice as many students as majors. So students seem to like the course, or they're taking it. It's reasonably popular. I think this year it's going quite well. That's maybe because Umut's teaching it instead of me. We found that the students really don't have a difficulty with the parallel concepts. Okay, what they have difficulty with is what they've always had difficulty. It's a data structures and algorithms course, so we teach recurrences. They have to solve recurrences. We teach algorithmic ideas, and they have the same difficulty with quicksort they've always had. They've, and merge sort. But the parallelism really doesn't seem to add much additional overhead in terms of the complexity of the course. We teach this in a functional style of programming, and the motivation here is we don't want to have to deal with the whole issue of race conditions. So if you call two things in parallel and one thing does a side effect and the other thing reads it, you have non-determinism, it's very hard to deal with. So we teach it in a way where you're not allowed to do side effects. And again, this actually turned out to work. We were quite worried about this because it's a non-standard way to teach a data structures and algorithms course. But we found out it's not such an issue. That most of the same concepts we've taught in an imperative style work quite well in a functional style. There's significant programming assignments. In fact, I'd say 80% of their time is on programming assignments as opposed to theoretical assignments. So it's not just a theory course. And we've made extensive course notes. I think now there's something like 250 pages of course notes, because there's obviously not a textbook on this topic. So what the students get are these course notes. They get the lectures, and that's what they learn from. And here's a detailed list of what's covered. I'm not going to go through it, but the key thing here is that many of the ideas are the same sorts of things you would learn in a sequential algorithms course. We do BFS, we do Dijkstra's, we do min-spanning tree. So they still learn everything they would have learned in the old data structures and algorithms, but they learn it all from the point of view of parallelism. So when we do breadth-first search, we immediately say, well, you can do each level of the breadth-first search in parallel. Right? It's not restricted to doing it on a queue one at a time. And this is just the idea of raising the level of abstraction. Right? If you really think about what's the abstract notion of breadth-first search, it's sort of doing one level of the graph from the source at a time. It's not putting it into a queue and pulling it out of a queue. That's a much lower level abstraction. Some of these algorithms are purely sequential. So Dijkstra's is just one where the work equals the span. So the critical path is as much as the work, and so there's no parallelism. Bellman-Ford has lots of parallelism in them. There's, when we get to min-spanning tree, we teach not the standard. Well, it turns out the Berufka, done in the right way, is a parallel algorithm. So we have to teach the parallel version of that. So basically, wherever something's parallel, we teach the parallel version. And for most of these things, they are highly parallel. For hashing is highly parallel. If you do it right, you can certainly look up the hash, and you can do the insertion if you're a little careful. So anyway, these are the topics, and we just do them with dealing with parallelism from the beginning. And again, we're not focusing on how to implement this in CUDA or in OpenMP, but rather at a high level.
Can I ask a quick question? So how do you deal in hashing with the race condition of updating table entries?
We have an operation on a sequence that says insert a bunch of things into the sequence. At given index, and it's defined such that the first one wins. So if a bunch of things hash at the same location, one of them will win, and then the one that didn't win might have to try again to find, for example, with linear probing, to find the next.
So you have sort of atomic abstractions.
That's right. We have atomic abstractions to deal with that. So that's a good question. Okay, so the last thing I wanted to talk about is, so this is all nice in theory. I should point out that the actual code the students runs sequentially. So they write the programs and in a parallel style with parallel constructs. But we don't have a good, we do this in the language ML, and we don't have a parallel compiler. But what we have done is we've gone and we said, well, let's say we did these ideas and wrote them in C++. Now, we don't want to have the students do them in C++ because there's all sorts of issues of race conditions, like I said. But it's just to get a sense of, well, what sort of performance we could get. And so we did this experiment where we basically generated a bunch of what we thought were quite wide variety of benchmarks of the sort that you would teach in an algorithms course, and also ones which go beyond simple algorithms. So we have a lot of computational geometry, we have ray triangle intersections, we've got the standard graph type algorithms, operations and sequences, things for machine learning, text processing, n-body calculations, etc. So what we did is we took these and we coded them all up in C++, but using a style of programming that we teach in the class, the sort of nested parallels at a high level. The particular language we use is actually Silk, which is an extension to C++ that's now part of the standard GNU release, G++ release. So you've got these things, and what these show is on a 32-core machine is one of these bars is the relative speed up to the parallel algorithm 1 processor versus 32 processors. So that's the higher blue bar here. Okay. The lower blue bar is the relative speed up of the parallel on 32 cores versus the best sequential code we could get. So this is the best minimum spanning forest code we could find, the best min spanning tree, the best maximum dependent set. And this just sort of gives you a sense that you get reasonable, you don't get perfect speed up except on sorting, but you get, an average of something like, 12 to 16 fold speed up. Okay, so you really can get good performance using this style of programming. And not only that, but, you get almost, in fact, every one case except one, you get at least a 10-fold. This is like 9.5 or something. It sort of argues that, well, you really, if you've got 32 cores and you're running on one core, you're really wasting that machine. You can get a full order of magnitude by using a parallel algorithm on every one of these, and in some cases you get 1.5 orders of magnitude. Anyway, so that's we just wanted to sort of convince ourselves that we're teaching them something useful, and I wanted to talk a little bit. So as part of this, I want to, in some sense, thank Microsoft because it was because of the computational center thinking that we even went down this line of thinking about parallel thinking, which led to the course. So I don't think this would have even happened without the original computational thinking center. And so I think in that sense it was very useful. There's also lots of specific interactions that we've had with Microsoft over the years in terms of parallel thinking. Recently there was a nice big data analytics conference at MSR Cambridge. I gave a talk on there. There's been there was a nice workshop that Judith Bishop organized with Don Syme at Popwell. I've been to some faculty summits, gave a talk at Redmond. We've been doing a lot of talking about possibly using F# in this course with Judith Bishop. And I think what we'd like to do is have a version, like I said, the course is supposed to be language agnostic. So in fact, our course notes don't use a particular language. It uses a pseudocode notation. Although the pseudocode resembles ML, which also, is F# is a variant of ML. But the homework assignments do use a language, and so right now they're in standard ML, but we've been looking at possibly doing a version of them in F# as well as a version of them in Scala. In terms of future, I think, like I said at the beginning, this course focuses on parallelism and not concurrency. So we ignore any issues of race condition. We don't discuss the notion of linearizability or serializability or mutual exclusion. These are all key ideas. And currently, if you look at our curriculum and most curriculums, these ideas are scattered a bunch of different courses. They're a little bit in our curriculum. They're a little bit in our 213, which is an introduction to hardware systems. Some of them in our operating systems course. Some are in our databases course. And so we don't have a coherent place that these are done. And so it's a little bit ad hoc. And I think this is very much the same as the idea of parallel thinking. There really are a set of core ideas here that could be abstracted away from particular languages and machines that all of us students should know, and in a nice, coherent way. And so what would be nice to do sort of a similar sort of thing here, where we take those ideas and wrap them up into a course. So that would be something to do in the future. I wanted to finish by, it turns out that if you look up parallel thinking on Wikipedia, I didn't do this until after I started using the term parallel thinking. How many of you have heard this version of parallel? It turns out that there's Edward de Bono. He's a very quite well-known person in these circles of management training. So you've probably heard the term lateral thinking. So he coined that term, and then after that he coined the term parallel thinking. And it's a particular approach to basically for large group discussion. That's particularly to come to decisions quickly. The idea is, I don't know, it sounds a little hokey to me. You put 6 different hats on, and you put your logical hat on, then you put your emotional hat on, and when you have your logical hat, the whole room talks about logical things, and you put the emotional hat, everyone they talk about. Anyway, it's popular, but what I found very interesting is that, Wikipedia says what it's really about is looking for what can be rather than what is. And I thought, well, if this is appropriate because, we're talking about parallel thinking here, it's not taking, there's really a focus in some cases of taking a sequential code and, sort of twisting it into being a parallel code. So it's, what is there, and let's work with what we have as opposed to thinking about, let's raise the level of abstraction and, think about what could be on this code. And I think that actually sort of as an approach to taking code and convert it to parallelism is a very important sort of thing to do, is instead of taking a sequential code and converting it laterally to something that's equally low level as parallel code, that's a mistake. What you should really be doing is taking a sequential code, raising the level of abstraction, like in the case of Quicksort, so where it's a more high level, where the parallelism sort of comes out more naturally. And that's going to have more longevity in the sense that parallel machines are changing very rapidly. So any code you write in CUDA is probably going to be worthless in 5 years. Any code you write in a lot of these languages are going to be possibly not useful. So if you think about raising the level of abstraction and having maybe the compiler map it down, that's a useful thing. Okay, that's all I wanted to say.
So I just come from Denver and supercomputing, where it's about some of these things, but they worry about race conditions, they worry about differential equations like Navier-Stokes equations. You don't teach any of that. I mean, where you have this sort of domain decomposition, not OpenMP, but it's MPI, message passing, and stuff like this.
So, yeah, probably what I should have said, I think all that stuff is very important. And so in particular, when I said, parallel thinking, is not these things. Those things are still important, but the point is that they should be taught, in our feeling, is after the fact, right? So that you can learn a lot of those concepts. One thing that I quickly went by here is one of the things we've been working on in the terms of the research side is how to come up with high-level models for accounting for communication costs. This is sort of capturing some of these ideas of how to deal with locality, et cetera, which I do think is a very important concept. So it's really just a question of teaching this first and then teaching a lot of these concepts. And some of these sorts of concepts you're talking about are probably not useful to all of our students, but rather to the particular subset of students.
But it doesn't. But the sort of parallelism that they use for these differential equations doesn't seem to be captured by your list of topics.
I would argue you're different on that, but we could talk about that offline.
We can argue, yeah.
Okay. Thank you.